Okay, today's quiz is on introductions to chemical equilibrium. And we indicated that it bridges from kinetics and into the equilibrium in a very smooth way. So the idea is for you to understand how the concept of chemical reactions moves from a kinetic phase into an equilibrium. This kind of equilibrium that we're dealing with here is, you may have heard, dynamic equilibrium. Meaning that for a reaction, reactants going to products, we have production of product as fast as the product is breaking down or going back to reactants in here. A static equilibrium, in contrast, is something that is not in transition, not moving. Okay, you in a car moving 60 miles an hour, set the cruise control, that's a dynamic equilibrium because something is moving. But when something is not moving, we call it a static equilibrium. There's a balance of forces all around. There's a balance of whatever makes this work in such a way that the reactions going left to right are kinetically as efficient as the ones going right to left. The point at which this begins, right here, signals the beginning of the equilibrium region. And that's why we call it extent of reaction. So this point is related to what we call the equilibrium constant. And it's given a capital K subscript EQ and essentially defines extent of reaction. Many applications can be developed around this K expression. It is based upon law of mass action, which says that opposite rates are equal, and hence that's where the quiz begins. So for number one, what does the law of mass action indicate? It simply indicates that you have rates of reaction forward equal to the rate of reaction in reverse. Forward, reverse. So if you chose a hypothetical reaction and wrote the rate laws for a reaction going left to right and the rate law for the reaction going right to left, those would be equal. A rate forward equals a rate in reverse. Typically a rate constant, say forward, or a rate constant in reverse is attached to the given equations that indicates that both processes are taking place. The answer, of course, is C for this one. I hope everybody understands that idea. The definition of the K value, of course, or what it defines, is extent of reaction. The equilibrium constant, that's number 2, KEQ, by definition, is extent of a reaction. How long does it take to get to this point in the concentration time graph? We will see reactions that reach that point in almost instantaneously and result in an extremely large amount of reactant left behind in the conversion process. And we will look at one today in the iron thiocyanate. That's just to the right quite a bit, and you'll have more product. As you increase concentrations of certain components of the reaction, you'll see the solution get darker and darker and darker, redder and redder. It's kind of a rust red color, but you'll see what I'm talking about. You're shifting that more and more to the right side and generating more product in the process. This one would be B choice. The essence of applying the concepts in equilibrium deal with you being able to write an expression, KEQ expression, for a given reaction. Now, equilibrium constants, while I'm introducing it, I'll call it a KEQ to emphasize equilibrium. But typically the K expression relates to the nature of the reaction. So you see portions of nature of the reaction. Now what does that mean? It means if you're working with reactions that are all gas phase, typically you would use a Kc. If you were using a reaction in solution that dealt with weak acids, you might use a Ka value. That's an acid ionization constant. Or weak bases would be Kb. Or the solubility relationship. Now, there's a lot to be said here. Called a KSP. Deals with how much of a salt will be delivered into an aqueous solution. So this dissolution is the term, meaning dissolving, of salt ions in aqueous solvent. Right there. So the point is, when we talk about extent of reaction or the K value, it all means the same thing. Essentially, if it's a large value, it means most of the equilibrium condition is products. It is a very, very small number, and we'll see both ends of this spectrum. It means that there is mostly reactant still present. And we reach the equilibrium point very quickly. It just, in seconds, is up and it levels off very, very quickly. So, in the nature of, in order to determine an equilibrium constant, we're not going to go through the development again, but you apply it in the following, let me write the equation, context. Say you're given an equation, nitrosyl chloride as a gas, say is in equilibrium with 2NO as a gas plus Cl2 as a gas, and I ask you what's the equilibrium expression for this, and I told you it's Kc expression. Kc. Well, when you write an equilibrium expression, now listen to me carefully, it's products over reactants. If we're looking at this equation, and I just make that statement, your first impression is probably these two, NO and Cl over NO. That's correct, because we're talking about the forward reaction at the moment. However, some problems will show up where you will need to take the reciprocal. In other words, we're talking about the reverse reaction. Now, what I wanted on here was the forward reaction, and I didn't say anything. I'm sure everybody did that. But the forward reaction expression is a concentration, the product of the concentration of products, molar concentration, divided by the concentration of the reactants raised to the coefficient powers. The coefficients will represent the orders of reaction, now in the equilibrium region. Now this represents the forward reaction. What represents the reverse reaction? If I was interested in the reverse reaction, two things could be done. If I'm given a Kc and I need the reverse Kc, all I do is take the reciprocal of the given Kc. So Kc reverse is equal to 1 over Kc forward. That is a valid question on exam day. Okay? So if I've given you Kc in this case is 4, the reciprocal would be 1/4 in the opposite direction. The H-was. The essence of an equilibrium constant in terms of what it means is more of a magnitude of the number. And I mentioned that just a moment ago. K equilibrium constants let's put it this way, greater than 1. Anything greater than 1 means you have more products and less reactants. So the concentration of products is greater than the concentration of reactants. And there are a variety of reasons you would need to know this, and it has to do with applications. But for right now, your understanding extends to this and this alone, that if it's greater than 1, we've got more products than reactants. If it's equal to 1, what does that mean? It means you have a balance of products and reactants. They come out even. If KEQ is, say, less than, equals less than 1, then the concentration of products is less. Concentration of reactants. We have extremes in numbers, and I just made up one here. It says, what does 10 to the minus 5 tell you? It simply says it didn't go very far in the extent of reaction, and very few products were generated. That means we're mostly reactants. So that would be B choice and the quiz. Finally, I gave you the synthesis of ammonia, and just as you picked out the equation up here, synthesis of ammonia reaches an equilibrium with 2 moles of NH3 gas. And again, all gases, we typically put a Kc value, and that's products over reactants. So we want to look at the NH3 concentration, gas squared, over nitrogen concentration, molar concentration, to the first power, and the molecular hydrogen concentration to the third power. And so that one is, looks like A choice. A choice in there, products over reactants. Yes. Any questions about that? Okay. The essence of this, please invest in these introductory comments, because we'll be applying those extensively throughout the rest of the semester, including thermodynamics and some of the concepts over in specialty topics like electrochemistry. And so I don't think we use it much in